Dear students, greetings of the day. Today I would like to discuss the applications of analytic functions. Let us see the definition of analytic function. A function f of z of a complex variable is said to be analytic at a point z0 if it is differentiable at z0 and also at every point of some neighborhood of z0. And there are a lot of applications from this analytic function. For instance, if you take f of z is equals to u plus iv as an analytic function of z, then in the context of fluid flow, the real part u represents the equipotential lines and the imaginary part represent streamlines. And the function f of z, which is the combination of equipotential lines and streamlines, are called the complex potential or complex velocity potential. Here it will be in the context of fluid flow. Similarly, in electrostatistics, the real part represents equipotential lines and imaginary part are going to represent flux lines, and the combination, the real part plus I times the imaginary part, is called the complex electrostatic potential. In heat flow problems, the real part is represented as isothermal lines and the imaginary part are going to be considered as flux lines. The function f of z is called complex temperature. A problem of great practical importance is that of determining streamlines when equipotential lines are given and vice versa. That is, given u or it is given u, it is required to find v such that f of z is equals to u plus iv is an analytic function of z. Now let us see how to construct such type of analytic function when the real part or imaginary part is known to us. And the procedure is given by Milne Thomson method, and we can see the working procedure of this Milne Thomson method. When the real part or imaginary part of an analytic function is given, we have to first find out the partial derivative of that real or imaginary part with respect to x and y. And as you know, when the function f of z is analytic, f dash of z exists. Therefore, we can express that f dash of z as dou u by dou x plus I times dou v by dou x. Once you find out the derivatives for the real part or imaginary part, you can make use of Cauchy-Riemann equations. That is, dou u by dou x is equals to dou v by dou y, and dou u by dou y is equals to minus dou v by dou x in f dash of z, so that everything will become known thing. That is ux plus I times vx, where we can replace vx as minus uy. After substituting for vx, that is unknown thing, we'll get a known quantity for f dash of z. And then the Milne Thomson method says that you have to replace x by z and y by 0. Once you do that, everything will be converted in terms of z. That is, f dash of z will be in terms of z. Now we just want to find out the integration of this f dash of z to get f of z. If we just integrate that f dash of z, we are going to get f of z. By that, we can easily segregate the real and imaginary part, and we can identify the real part or confirm ourselves that whether it is matching with the given problem as real part, and similarly the imaginary part can be obtained. For example, if f of z is equals to u plus iv is the complex potential function, Construct the analytic function w of z or f of z, whose potential function, which is represented as real part u is equals to log of square root of x square plus y square. And they're also giving you to find out the flux function v. Here we have the real part u, which can be taken as half times log of x square plus y square by the property of logarithm. Then find out the partial derivative of this u with respect to x and y. Ux, that is dou u by dou x, gives you x over x square plus y square, and partial derivative of u with respect to y gives you y over x square plus y square. Now we know when f of z is analytic, f dash of z exists. Therefore, f dash of z can be expressed as ux plus I times vx, where we don't know about vx, but by Cauchy-Riemann equation, vx can be replaced as minus dou u by dou y. Once we replace that in your f dash of z, both the quantities will become known quantities. When we use that Milne Thomson method, which says you have to replace x by z and y by 0. Once we do that, we can see that f dash of z becomes a function of z. Here it is z over z square plus 0, and the next term here, which is associated with I, is completely 0 because of the numerator term y is 0. Thereby we get f dash of z is equals to 1 over z. And once we integrate this with respect to z, it gives you f of z, that is becoming log z here. And also we know log z can be expressed as log of r e power I theta, that is the polar form of x plus iy. And if you segregate that log r plus log e to the power of I theta, we get the real part as log of square root of x square plus y square, and the imaginary part as tan inverse of y by x. This is how you can use Milne Thomson method to construct the analytic function, or also it can be used when the function f of z is analytic and you know only the real part or imaginary part. Let us see the next example where they are asking you to find out the analytic function f of z when imaginary part is known. The same idea will be utilized. Differentiate v partially with respect to x and y, and then substitute it to f dash of z, where f dash of z is nothing but dou u by dou x plus I times dou v by dou x. Here in this case we don't know about dou u by dou x, but dou u by dou x by CR equation we can replace it as dou v by dou y. Once we do that, everything will be known. So let us substitute that vy plus I times vx, and you can use Milne Thomson here that says x has to be replaced by z and y has to be replaced by 0. Once we do that, f dash of z will be completely function of z. Here in this case it is becoming e power z multiplied with z plus 1. By making use of integration by parts, that is integrating on both sides, here f dash of z on integration becomes f of z, and e power z multiplied with z plus 1 on integration gives you z e power z plus c, that is on complete simplification. Now if you want to get the real part, you just have to replace z as x plus iy and segregate real and imaginary part. That gives you the real part of this analytic function f of z. Similarly, few more examples are given here. The next example says that find the analytic function whose real part is given, and you have to determine v also. In the same case, first you find out the derivatives of the real part u with respect to x and y, that is partial derivative, and substitute it to f dash of z, make use of CR equation and use Milne Thomson method, replace x by z, y by 0, get f dash of z. On complete integration and simplification, your f of z is going to be z square minus 2 by z plus c. Now if you segregate the real and imaginary part, we can easily obtain what is this v for the given problem. That's all about this construction of analytic function. Thank you.